till the last lecture we have already discussed the main concepts of mechanics, and in that we have mainly discussed about three specific arrangements of beams. The first one is, as you can see here, that the axial stress, that you have a cantilever like this and then we are applying the force in this direction, right, we are pulling it, okay, pure axial stress. And then we discussed about transverse stress, right, where I am applying the force in this direction from the top, correct, from the top I am applying the force. And then the last one is the guided beam structure, where we are fixed at one end and another end is also fixed, but this fixed thing is, or fixed reference frame is moving like this, right. So, the beam can bend or deflect, but not at this point, it cannot have a slope, it is like this. And all of these three cases, the axial stress, transverse stress and also the guided beam, all of these cases we have calculated the spring constant. And what we do with the spring constant, then we saw that one example in one of the previous classes. This example we saw in one of the previous classes, that once we know the axial like the stiffness constant for one particular beam, and then whatever arrangement we have, like with multiple beams, just we can apply the parallel spring or the series spring in series formula and can get the equivalent displacement or equivalent spring constant, right. And from that we can back calculate the force. And in last we found out, like for the guided beam structure, we found out this formula, that Kb is equal to 12 yi by Lq. So, that is the stiffness constant for a guided beam structure. And now we will see one example where we will see that how we can apply this expression and can calculate the deflection for a particular proof mass or for a particular structure. So, now we will see this example where we will try to explore how the guided beam structures actually work. Okay. So, for that I have shown this picture, that this is the central mass, which this is called a proof mass, okay, and then this is connected to several beams in this arrangement. Now, see these beams I have named A, B, C, D. All these four beams are of same width, same length and thickness, okay, and across this dotted line or the central line along the y axis, both the sides are symmetrical, though according to my drawing it is not, but you can assume it to be symmetrical, and both the sides have same dimensions, same arrangements. Now, this shaded line, black shaded lines are the one which are actually fixed, okay. So, this point is fixed, this point is fixed, and on the other side this point and this point is fixed, okay. So, these four beams at one end it is fixed, and rest of the structure is not fixed, okay, rest of the structures are moving. Now, these are slender beams, whereas these are thick beams, right. This side it is thick beam and the other side also it is thick beam. Let us say name it something like say name it P, Q, R, S, and this is, let us say, E, F, G, H, okay. So, as I was saying that A, B, C, D are slender beams, and slender beams means this will bend, okay, and P, Q, R, S are like the stubby structures which will not be able to bend or twist. Now, this proof mass is suspended, it is like this. This proof mass is suspended, and at the end this is connected with several legs, right. So, this is the proof mass, and then you have these arms connected, and these arms are fixed somewhere. So, this proof mass can move in a y direction as well as in the x direction, and accordingly these beams A, B, C, D, E, F, G, H will bend, okay. And what we need to find out is what is Ky, what is ky? Ky means the stiffness constant in y direction, means if this is the proof mass and I apply some force here in this direction, then how much will be the deflection, right? You know that Fy is equal to k into, let us say whatever is the deflection in y direction, the deflection delta. So we need to find out that ky. Okay. Now how this is a guided beam, as you can see here, this point, let us say if you take one particular beam like B, then B beam is connected to the proof mass. So one side it is connected, it is like this, one side is connected to this beam, okay, and this side also it is, as it is fixed to the proof mass, it cannot have a slope there, the slope is 0. On the other side it is connected to the PQ stubby structure, which also can move, but it cannot have a slope or bending at this point B. So ultimately if I consider the B beam across the proof mass and the P point, then it will be like this somewhere. So this is like guided movement, okay, this is like guided movement. So here this proof mass is moving, so let us say this hand or my right hand is the proof mass and the other side this is the stubby structure. So though it is moving, this is also moving, but this is not moving as much as the proof mass is moving, okay. So but and both the side the slope is fixed and that is 0. So it will be something like this, the movement will be like guided beam. And similarly like B, all the other beams like A also, you see that A is one side it is connected to PQ, which also will have a slope 0 at that contact point, and the other side it is already fixed. So this side also will have, even the deflection is also 0 and the slope is definitely 0. And C and D beam is also like A and B, okay, and EFGH is just the symmetric part like the other part or of ABCD. So all of these beams are under guided movement. So now we know that these are all guided structures. Now for the guided beam structures, we have already calculated the stiffness constant, and that stiffness constant is this term, that Kb is equal to F by W into 12yi by L cube. So now we will put this, we will use this here. So for guided beam structure, for a single beam we know, let us say for a single beam Ka is equal to yi by L cube. So it is 12yi by L cube. Now y and L are given and I we need to calculate, and for this kind of beam, so y and L are known and I need to calculate. We need to calculate the area like the inertia or moment of inertia, right. And for this kind of geometry, we have already seen that the I is equal to BH cube by 12, right, and there H means the height or in which direction the force is applied just perpendicular to that. Like, so if this is a beam, if I consider, then if this is the force applying, then H will be this thickness, right. And in this beam, in our case, for this example, force is applied in y direction, and so this W or which is actually the width, that is the height here, right. So and the thickness is actually perpendicular to the height, thickness is actually perpendicular to the force. So here I equals to T W cube by 12, and accordingly we get that Ka equal to y T W cube divided by L cube. Both the 12s gets cancelled out. So YT W cube by L cube, and this is the stiffness constant for all the beams, because all the beams have the same dimension. Now what we need to understand, that how these beams are arranged, which beams are in parallel, which beams are in series, and accordingly we can calculate the equivalent stiffness constant. Okay. Now we need to very carefully understand that how these beams are connected. See, this is the proof mass. This is the proof mass, okay, and this proof mass is connected to the this B beam and D beam directly, whereas A and C is not connected to the proof mass directly, right? Now let's assume if the proof mass move upwards by 5 micrometer, then not necessarily this PQ also will move upwards by 5 micrometer, because this is not under the same force. Okay. Now let's say because the proof mass is moving upwards, we are pushing the proof mass in the upward direction for 5 micrometer, then the beam B and D starts to bend upward, and because of that it starts pulling up the PQ structure also, and because of that, let's say the PQ structure moves by, let's assume that 3 micrometer. Then if the PQ structure moves upward by 3 micrometer, that means the B beam has bent, but both the sides has a bending or the separation of 2 micrometer, because for the B bending, for the B beam, this point which is connected to the proof mass has moved upwards by 5 micrometer, whereas the other part which is connected to the P structure has moved upwards by 3 micrometer. So it has a guided movement of about 2 micrometer. Okay. Whereas as the PQ structure is moving upwards by 3 micrometer, then the A point, for the A beam, this point which is connected to the PQ structure will move upwards by 3 micrometer, but the other side of the A beam which is fixed will have no movement. So in that case, then the A structure has moved upwards in guided direction by 3 micrometer. So the point here is that A and B is under the same force, but the deflection is not same. That means A and B are in series connection. This A and B are in series connection, where the deflection may be different, but the force is same. Okay. Now if I draw this structure then in a spring mass arrangement, so this is A, this is B, and this whole platform is moving upward or downward. Okay. So this is the B side which is connected to the proof mass. Okay, it is connected to the proof mass. So now you see that A is connected one side to the fixed and another side to the proof mass, and now it has the same force, but deflection may be different. Now the interesting part is that if you see the CD arrangement is also connected to the proof mass, and another side it is fixed. So if I now draw the CD arrangement, then the beam D is connected to the proof mass and beam C is connected to the fixed point. So ultimately, because it is connected to the same proof mass, so the combined deflection of A and B and combined deflection of C and D will be same, right, like in this picture. And in that case, what will happen, that this arrangement, this AB arrangement and this CD arrangement is in parallel. In that case, what we will find out first, the stiffness constant for the one side of the beams, that is ABCD. So we know that this is the formula, that Ka is equal to YT W cube by L cube, right, and from the series and parallel formulation of spring mass system, we know that for A and B, which is in series, then KAB, if we consider the equivalent stiffness constant to be KAB, will be 1 by KAB is equal to 1 by KA plus 1 by KE, 1 by KA plus 1 by KB, and let's assume both to be K. Okay, so 1 by K plus 1 by K, it is 2 by K. So KAB equals to K by 2. Again AB and CD is in parallel. So KABCD, the whole left hand side of the structure, is equal to KB plus KCD, KCD, and KB equal to K by 2. Similarly, KCD also will be equals to K by 2, and here then we can get that the K by 2 plus K by 2 is equals to K. Stiffness constant in one side is K. Now we see that this is the stiffness constant K is for one side, right, and for the other side we have the exactly same structure. So if EFGH, all these beams will also have the same stiffness constant, that is K. Now this is the proof mass. Now this is the proof mass, let's say, okay, and one side it is connected to this beam which is KABCD, and another side it is connected to the beam which is KEFGH, right, and both the side it is fixed to the other ends. Okay, and how these beams are connected, already we saw in the previous example that these are in parallel connection, because it has the same deflection but the force may be different. However, for this case KABCD and KEFGH both are K, both the stiffness constant are K. So the force and deflection both are same. So the ultimately equivalent KY for this kind of system is KEFGH is equal to 2K, and if I now put all the known values of K, so let's go back, K is equal to YTW cube by L cube. Now if we put all the values of Y, T, W and L as we have already know, so then it will come as 150 into 10 to the power 9, this is the Young's modulus, then 3 into 10 to the power minus 6, this is the thickness. One thing here, probably I have wrote these things as millimeter, this is not millimeter, this is micrometer. So YT into W cube, W is 5 micron, 10 to the power minus 6 divided by L cube, L is 200 micron. So is equals to 7 equivalent to 7 Newton per meter, and then Ky or the stiffness constant is 14 Newton per meter. So now it means that if for this beam or for this structure, if I apply 14 Newton force in y direction, then the movement will be 1 meter, or 14 micronewton force, then the movement in y direction will be 1 micrometer. Okay, so we get the stiffness constant for this kind of beam, and the advantage for this kind of structure is, or this analysis is now this can be a sensor, right? And for this particular sensor, let's say if it is a force sensor, then we can measure the deflection. If we measure, let's say the deflection for this particular proof mass is about 0.5 micron or 500 nanometer in y direction, then we know that the force has been applied is 7 micronewton, right? So this is how we can calculate, and with that we will close this module. Thank you.